Hello, everyone, and welcome to this webinar on our newest add-on to MapleSim, this one focusing on web handling, modeling, and simulation. So in this webinar, I give a introduction to this new library and talk about what can be done, the type of systems that can be simulated within MapleSim with this library, and type of questions that one can get answered to doing this type of simulation. So as for the agenda for this webinar, I'll start with a overview of the web handling component library in MapleSim. Usually don't get into much of the equations and details, but here the web description equations or equational motion is very important and compact. So I'll talk about them, those equations, briefly, then move on to a example especially for those who might not have previous experience with MapleSim or a tool similar to MapleSim, how a modeling process would work. We'll do it step by step together. And then I have a number of examples. I think I have 6 in total that, depending on how much time remains, I'll go through them. And at the end, I'll talk about the code generation, which kind of brings this whole exercise and modeling and simulation full circle, very, very briefly, to leave you with some ideas. So without further ado, let's get to the topics. First, an overview. So the web handling library is going to focus only on the planar systems from a mechanical standpoint, or the machine direction from the web handling language. It's for one directional flow from upstream to downstream, from source to sink, or from unwind to rewind. That's the process that we are going to simulate with web handling library in MapleSim. And the focus of the library is system dynamics. The library allows you to consider all sort of different things regarding the dynamics and of your system, how it comes to a steady state, and what transient it goes through. In terms of features, obviously this library is compatible with the rest of the MapleSim libraries. So you have actuation, you can use an electric motor, you have or hydraulics, or other types of controllers, signals. You can bring them together to create a comprehensive and complex model. But as we know, models are created to answer questions. So we select domains and details according to what type of a study we want to perform. The library is created with simplicity of model creation in mind, and hopefully that will come true in the rest of this webinar. It includes all sort of rollers with no slip conditions or with slippage included. So that's a big feature of the library. And it includes both wind or rewind and unwind drums, and also includes simplified source and sink to basically cut off or focus on portion of the web line. And we will see a lot of examples that this comes handy. You don't want to model the entire web, you want to focus on part of it. And this source and sinks allows you to define the boundary condition of the portion you're looking at. And measurements. So tension, you get access to tension everywhere, and you can also visualize it. And I have examples of how that is done as well. So the library is part of MapleSim available libraries as an add-on. For those who have worked and used MapleSim, already comes with a base set of libraries like signals and multibody and hydraulics, pneumatics. And a number of add-ons are created, the web handling sitting at the bottom. The newest one that allows for easier creation of models in specific domains. As you can see in that list, a little bit higher, there's tires, ropes and pulleys, drives. So specific domains that will require more work to build up from simplest components. We tend to provide additional value with creating add-on libraries, and web handling, as I said, is the latest in that list of add-on libraries. So the library itself includes the web probably the most important, which basically you have a web material properties that you have to add to every model that dictates all the web span components that you have, how they're going to behave. The rollers, as mentioned, both nip rollers and idler or pull or with slip, without slip are included. We even have, and in the middle there, an ideal point or node that allows you to manipulate or affect the conditions of the web from one side to another without really bothering with the dimensions and sizes and the wrap angle and things like that. It could come handy for more simplified or abstract analysis. Sources and sinks, wind, unwind drum, and the boundary conditions that you can use to, as I said, focus on portion of the web line. Some sensors, we will see examples of that. The load sensor that it somewhat mimic a load sensor on a bearing on an actual roller for tension measurements. In simulation, you do have access to tension wherever in your model that tension is available. But if you want to use a somewhat similar or mimic the process of load cell and see potential errors in the measurements, factors that could affect it, this component could become handy. We'll see an example of how to use that as well. And there's a subsection for primitives. This is the library that allows you to move things, place things on the screen, and like on your actual 2D space. These are, for those who have seen MapleSim, these are borrowed from the multi-body library, but made such that they are simpler and only you have 2D parameters to set. Certainly you can use the multi-body, but just don't use Z. But these components makes things easier. So let's jump into some theoretical work. In most publications or research publications on the topic of web handling, if not all of them, the process starts with selecting a control volume over the span. There are some details and intricacies that we are going to not include here and just focus on the most important parts. So we have a span that material flows in and goes out, as the rollers show, the material is assumed to go from left to right. So the tension on the side A is TA, the tension on side B is TB on the boundaries. The velocity of material coming into the control volume is VA, and leaving the control volume is VB. With these assumptions, we can write the conservation of mass. This integral equation has a lot of terms, but we will quickly simplify that. Before doing that, let's take a look at the terms. So this one is density at side A, density of the web, area of the web on side A, and the velocity of web on side A entering to volume, control volume. And the other one obviously is everything else going out. So we're assuming the change in density, change in area, and change in velocity. So if we have the material coming in, subtracted from material going out, this is the rate of flow rate of material. So what we are left with is the rate of change of whatever is inside. And that whatever is inside is done by the integration over the span. But we are going to immediately make some simplifying assumption that takes care of some of these detail here. We're going to assume that over the span, things are constant. So a strain in the material remains constant, velocity remains constant. So there's a change of velocity as the material enters the control volume, but on the control, inside the control volume, tension is constant. So TB, epsilon B or strain is the same. So with that, we're not dependent on time. We are dependent on time, but we're not dependent on position. So we can immediately simplify the integral. And if we now, because we are only dependent on time, we can simplify and not include the time notation for simplicity. And we get this simple equation. So this now has, everything is time dependent, but let's see what we can do with this. Obviously, L is the distance, but in terms of the integral, it's the integral over the length. So it still represents the length of the span, and it accounts for when the rollers are actually moving. We might have a change in velocity, but we might actually have cases that the rollers are non-stationary, and we'll see examples of that, like in the case of dancers, for example, or accumulator. So let's look at what else we can add to these equations. Two common sense pieces of information. The first is that if you grab a tiny piece of web and stretch it, the mass of that piece does not change. I mean, it won't evaporate or get added. So that's what the first equation there is, U being the index for undeformed. So that's all it says. If we stretch a piece of web, the mass in it does not change. And the second equation defining the strain in the machine direction. So putting this together, we can find a relationship between unstretched state of the web and its stretched. So now we can write this equation for side A and side B. So we have row B, AB, and row A, AA. And if we put it in the equations that we just simplified, we get everything based on undeformed states, and those are constant. So we can simplify that and get to this simple equation as a result, which is the basic or fundamental equation describing the velocity, tension, and deformation of the web. In a lot of work, they go further steps at this point and linearize this. We don't need to. We'll let MapleSim deal with this nonlinear equation as it does very efficiently. The two other equations there are the tension strain relationship. Right now we have a linear elastic material included with the option to include the change in the area cross-section due to the existence of Poisson ratio. This value is really negligible. So the default Poisson ratio is 0, but you can put any reasonable number there. For the strain ranges that we deal with, that turns out to be not at all significant. So now these equations are become the fundamental form. We add one more term for extra damping to this, and that is most cases not necessary. In some cases, it might help with describing the behavior of the material, but in most cases, including a little bit of damping helps with the numerical stability and speeds of integration. But it's an optional parameter that can be set to 0. So the first parameter in the library covers these pieces, parameters required for these equations that describe the web. We have the width, we have the thickness, the density, the modulus of elasticity, the damping ratio, and the Poisson ratio. As I said, you will put one web block on every model, so that defines all the properties for all the pieces of a continuous web in your roll-to-roll model. With that, let's take a look at what it will take to build a model with the web handling library and MapleSim, this block diagram approach with component that represents rollers, webs, and positions and rotation and things like that. So for that, I selected a rotational dancer. The focus is only on the rotational dancer, not the upstream or downstream sections of the web line. We have 4 idler rollers and a rotating arm in the middle, and boundary condition for material coming into this model of ours and the material exiting. So first thing we do, we look at the library and say, okay, what do we need to put this model together? We need the source and sink. So those two, we grab those. And we need rollers. So each roller has option for configuration, whether we want the web go on top or on bottom. And very easily from the diagram that is in front of us, we can decide which one to use, and the icon changes. So there's a switch that you select, and the one that matches your expectation, you keep that. You run the simulation, and if it's you made a mistake, you can rerun the simulation and select the right configuration. In this case, it's fairly obvious what we are looking at. So that's the rollers and the input and outputs. The next thing we need to do is obviously add the web span to this. Web spans are the glue that connect everything together. So we have 1, 2, 3, 4, 5 spans between these input and output and the 4 rollers. Now that we have brought in our spans, we need to anchor things where they are to the ground. So we use the fixed frame and connect rollers and sources and sinks to the ground. Each component, and we will take a look once we go to the tool, has parameters like this fixed frame will have X, Y, and theta for defining the position and orientation. We don't have orientation changes here, so we'll put the right X and Y such that each piece is in our model appear at where it's supposed to be. And I mentioned this maybe a couple more times as we go forward. The placement of components on the canvas in MapleSim has no bearing on your model. You define where they are by the parameter values, not by how you arrange them on the canvas. The arrangement on canvas is just a visual aid, so you can find your model better or figure out how it works if you're passing it along to someone else. So what else? We have anchored the most components, but we still have 2 idler rollers that are not connected to anything. We need a pivot so that we can connect those 2 rollers to that, and that pivot exists in the primitive. So we have a revolute joint. In this case, will be our pivot. What else we need? We need to have an offset for the rollers because they are not at the center of the pivot point. They have an offset with a certain length. So we'll select an option for add and frame offset. So we put half of that link to the one roller and the other to the other roller, and connect them all to the top frame of our revolute joint. So now we have all the pieces that we have. We just need to connect them together, and we can do that by dragging them and then connecting the connections between the appropriately colored ports. And as you can see, the model is now animation of it is running is shown. And notice that on the downstream, the tension is being increased gradually over time, and that increase in tension, let me play this one more time, that increase in tension translates to increased angle of rotation of the arm, which is this revolute joint, but also has a spring in it. So it will resist, and based on the tension and the in the compliance, one can estimate the tension this way as well, or have a measurement of the angle and use that in a feedback loop. And we will see another example of a dancer and how that information is used in a closed loop control. Some of these design, I'm just going to complete this example that I've seen include maybe a bit of a storage that goes along with the rotational dancer. So let's look at the diagram. So let's say we want to do this with adding 2 more idler rollers. And at this point, we should be able to figure out that the order of that the web goes through, we would basically need them added in between these 2 components, because that's the web. From the web standpoint, they are between these 2. Although they are left and right, and from the block diagram approach, that's what the models would look like. And so we can add these 2, figure out the going on top or going on bottom, and by putting the right dimensions for the diameter of the rollers, and even inside diameter if you want to have lower inertia, and the position, we can complete the model and go about the design process that we originally intended. So I included this this kind of worked out example to give you a sense of how a model comes together from a block diagram approach, where we connect the plan out the model, we we place fixed rollers where we want to put them, and anything that moves, we come up with a way, is it a linkage, an arm, a slider. We use either the primitives inside the web handling library or the rest of the MapleSim libraries to make sure that we capture the motions and dynamics exactly as we want them. And you notice that the web spans sit between everything, and they're color coded so you don't make a mistake in connecting them. So green to green, blue to blue, and that's a convention that must be followed. And as I mentioned, it's always from left to right, positive x-axis. Our models are sitting in an xy plane with z coming towards us. Okay, so now I am going to jump into MapleSim and actually look at a few models together. The models that I have selected for this segment of the webinar hopefully will be able to highlight the features that are included in the web handling library. We're going to look at a disturbance propagation model where we have a slippage, and that slippage allows the downstream error in speed travel upstream. Then we'll see how we can minimize that. Obviously, this is a hypothetical example and might not be, there might be other ways to fix this problem, but here as an exercise, we're going to go through that and see some of the features of the tool. We're going to look at a load cell and the second example, and how we can use the reaction applied to the load cell, which will include both the tension and the weight and the angles, and work out the tension, and then check it against the exact answer we get from the simulation itself, and see what factors would cause error in the measurements if we use the load cell. Still, this will be simplified, that some of the noise and other factors might not be there, but it will capture systematic issues that you might face in that deployment. An interesting example that is selected to show that we can cover variable wrap angle. All rollers provide information about what is the current wrap angle, but that wrap angle can also be dynamic depending on the system. And some extreme example is selected here to kind of highlight that. The other examples that I have, as I mentioned, we're going to use the other type of dancer, and this time we complete the model for an unwind system that goes into higher and higher speeds, but we want to keep the tension as steady as possible. So a PID controller is used together with the dancer to accomplish that. The systems, these are dynamic systems, so they could go through resonance. So we have an example of showing how a system is set up, and then further post-processing on the data is done in Maple. Obviously, I won't be able to go deep into Maple, but there is a whole host of applications and expansion and enhancement that you can do in your modeling and analysis work that can be done inside Maple, pre-processing and post-processing, and equation analysis. We will look at something very simple in a form of post-processing the results to get a frequency response. A more detailed or elaborate model, we're also gonna, the last model we look at, and that model would be our segue to code generation and dealing with FMUs. So with that, let me stop the presentation and go to MapleSim. So here's the first example. I'm just gonna open the library so that we have that as reference. So here we have, let me set up the situation that is captured in this model. We have pulled rollers, all are being driven speed control at a constant velocity. So nothing special here, except that we designated just for an exercise that this one would slip. For some reason, this one can slip, And this one suffers from a very bad case of velocity, sinusoidal velocity error. Realistically, this could be some misalignment that could cause this, but it is very important that this section of the web does not suffer from tension variation too much. But as we all know, with the slipping rollers, this can happen. So if we look at the results, this is the plot of the tension in here. Hopefully you can see my mouse. So this is the roller that is slipping. This is the roller that has the velocity error. And this is the tension area that we really don't want to see such a fluctuation inside. So here I have a playing back the simulation, and I'm using the color option in the library to kind of demonstrate the change in the tension. Obviously, the plot on the left side also shows the same thing, and we can see that because of the slippage, the tension on either side of the slipping roller are the same. So there are many different ways to deal with such a situation in practice. Increase the tension in the line. Some of them, or maybe most of them, might not be applicable to all cases. Increase the wrap angle, do alternative designs. But one way, just to showcase the feature in the library, is to add vacuum. So under the friction section of the component parameters, we have the vacuum pressure. And in this case, the model actually recommends about 30 kilopascal. So let's just put that in and re-simulate. Before doing that, so I have 30 kilopascal suction added in there. So I'm going to just save this as original. Right. And now I'm going to rerun the simulation and hopefully be able to compare the results. Okay, so we're going to just rerun, nothing else changed except that adding some suction to that roller with slipping, which increases the normal force. We have the formulation for the friction, and that will increase the friction force and tries to minimize the speed error between the web and the roller. And that would result in better isolation for the upstream section. Obviously, if we selected no slip, there would be complete isolation of any disturbance downstream. So we'll just wait for the simulation to finish. So here we go. As expected, this new line, the red line, and I'm just going to save that as new so that we can quickly find them. So we can see the new is having a lot less variation. It's going to turn off the display of the original so we can look at the colors. Might not be as visible. I selected a very narrow range for the change of color, but you still can see that this one is not changing as much as this side with the error is. But just to demonstrate the process of having a slippage, the consequence of a slippage, and one potential way to deal with slippage if it's applicable to an actual case. Quick look at the slides. So the next example would be load cells and web tension. So that's my second example. So here, let me just show the 3D first, and then we'll talk about the diagram itself. So we have a system. We are visualizing the actual force arrow, the reaction on the roller with the load cell. And the plot that you see on the left, there are actually 4 plots here, and I'm going to zoom on a section of it so that I can talk better on what we are looking at here. So the red and green plots are the actual simulated tension on the either side of the idler roller with the load cell. The yellow or gold plot is the estimated tension using the horizontal portion of the load cell. And the blue line is the estimated tension in the web at this section using the vertical portion of the load. The equations for this calculation is pretty straightforward, depending on which one you use. So one, if it's vertical, you need to account for the mass of the roller as well. But the horizontal one doesn't have that, but one might not be applicable depending on the angles. So what we are doing here is using this inclinometer sensor to get the actual angle. We obviously could work out these angles by hand based on the position of where things are, but we can use these sensors to simplify that work. The load cell is just a support with extra sensors in it and provide us with the horizontal and vertical. And these block diagrams with sine, cosine, inverse basically just take care of these equations. Now, before I move on, let's have a look again at the plots. So we see here that the estimates are pretty good. The exact solution coming from simulation and what we were able to get from the load cell calculation were okay. But in this portion where we are accelerating, they're not okay. And that should be quite expected, because during acceleration, these rollers have inertia. And because they have inertia, they would create tension difference, and that amounts to error in the measurements. That extra force is not accounted for in this simple static derivation. But as soon as we hit the steady state, that error goes away. The other source of error could potentially be the friction in the rollers. So for example, if I add a bit of viscous friction to all the rollers, as you can see that I parameterize the bearing viscous friction here on all three either rollers. So they're really poor bearings right now. What we would expect is that obviously MapleSim simulation will still give us the exact tension, which will be different from left and right, but the estimate produced by the load cell calculation would be worse. And that is also expected, as there is going to be, even at a steady state, difference between the estimated values. And that's to kind of emphasize the dynamics are included, and all forces that you would expect is included in the simulation as an example of how the system would work. The next example that I have is the variable wrap angle example. As I mentioned, this is quite an exaggerated exercise just to demonstrate. So here, very similar to that dancer that we have seen, we have a big, but this time a big roller in the middle and two either on either side, but we are rotating them with respect to the center of this roller. So that will change the wrap angle around the big roller. So let's have a look. Actually, better to do a front view. And maybe I make this a bit bigger so we see a little bit more. Okay, so let's reset. So as we see, the simulation starts, and first we move down the left arm, creating a bit of a tension variation, but then things settle down. And now we're doing the same thing to the shorter right arm. And you can see in the plots on the left, we have the wrap angle as measured by the components. So it for the big roller reaches up to 280 degrees. And during this time, because the roller is not driven, there is a dip in its angular velocity, which then recovers due to the slippage and the friction between the web and the roller. And during this process, we have some variation, a minor variation in tension that is also captured by just plotting the tension in all four spans, 1, 2, 3, and 4. So one is very tiny, but it's still a span that we can measure So this kind of gives you an idea of if someone wants to go detailed, they can. Two things that I want to signify with this example. One is being able to change the wrap angle during simulation, during a run, and also couple that with more. We don't have to couple that with a detailed calculation of the slippage. We can use simple slippage model, but that is possible to combine and create more richer simulation models. Okay, moving on. The next example, as I promised, is a control system with the dancer. So let me go back to MapleSim, and this is a web tension control. By now, we should have some familiarity of how things work, and even by looking at this diagram, start to make sense that what are we looking at. We have a roller on a frame, so this has an arm that this roller is at end of it. This arm is connected to a revolute, and that is rotating. So that's very, very quickly we identify that this is our dancer. This is our sensor for the angle of the dancer arm. We have a gain, we have a desired tension, and a controller that based on the error feeds a value to a pure torque value as a simple case here, but this could have been replaced by a brake to complete the model that way. The calculation involves the stiffness in the dancer arm, and that stiffness here is done very simply as a rotational stiffness. In a more realistic scenario, you might have a pneumatic piston cylinder to provide that resistance, or different ways, or even a weight to do that. But in this case, we have a torsional spring, and with some calculation between the masses of hanging parts and the angle of rotation and preload, we can come up with an angle that is linearly, almost linearly proportional to the tension, and then use that to do a feedback control. So here, as I'm running the simulation, we go through the initial setup, steady state, and so the things that are happening right now in the model are few things together. First of all, the desired velocity downstream is increasing. It's going from 2 meters per second to 5 meters per second. We want to keep the tension at that point as steady as possible. As we are doing that, the radius of the roll is decreasing, which affect the relationship between the torque of the brake and the tension. And also, as a result of decreasing roll diameter, the inertia of the rotating part changes. So all of that are happening together, and these are all accounted for. And with the really minimal tuning, obviously this can be improved, but we were able to more or less, under these rather harsh conditions, keep the tension in the line near 200 newtons, which was the desired value set by the this maximum here. So that's an example of how we use other components like the PID or gain or a sensor to expand the model and include other pieces to it. As you will see towards the end of this presentation, we, instead of doing this, you might just export the model as an FMU or as a digital twin of your system and use in your automation environment to test your controller against that. So that's another path that this type of modeling can take, thanks to MapleSim capabilities of generating efficient code. So that's the next example that I have, looking at the time, is the subject of resonance, which could be a problem depending on this type of system that you have. We in this example, we have something very, very simple. We have two idlers. Again, we look at the portion of the web line only. We have constant upstream conditions, the tension of 100 newtons and the velocity of 1 meter per second. But for the purpose of this analysis, we are putting a chirp signal on the velocity very small value, about 1 millimeter per second on top of the baseline 1 meter. And we'll see the effect of this frequency sweep has on the tension in this span. We could have looked at the angular velocity of these rollers because these are no slip, so it directly represents the dynamics here, or any other tension in the system. But we chose to look at this one. So when we run this simulation, as the frequency of the chirp increases, the tension in this segment clearly goes through two resonances. One significant, the tension goes as low as 0 and as high as twice the baseline tension, and that's important to consider. But the main purpose of this example that I've included, aside from again emphasizing the dynamics of the system, is included in this type of simulation, is that we can do some more rigorous post-processing on the results. And for that, I've already have a Maple worksheet attached to my MapleSim model. And Maple worksheet is a great way to enhance a model. You can save it with the model itself, where you have your theory, your applications, your design guidelines, and calculations are all stored there. Here we're doing a post-processing on this result, this tension that is measured from the model. We are going to do some post-processing on it. So I'm just going to double-click on it. We'll open Maple. And so I'm going to zoom in a little bit so the font is better visible. So the first line establishes a link. The second line establishes the simulation setting. We're going to simulate for 20 seconds. We're going to sample at 100 hertz so that it will give us coverage over 50 hertz. So the next line is just simulate. So we simulate the model, very similar to hitting the play button in MapleSim, but I'm doing that programmatically. This provides a lot of flexibility in mechanizing group simulations, comparisons, and having a central hub for dealing with parameter variations and model variation in one place. So now that we have the simulation back, we just do a plot, which is exactly like the plot we got from MapleSim, but we now have the data and we can do things with it. We select the data as the probe for the result number 2. The result number 1 would be time points. We're going to do a Fourier transform of the results and then plot that against the range of available frequencies. And that will give us this nice plot that clearly identifies the two resonant frequency of our system, one being around 19.95 hertz or 20 hertz, and the other one is 34.55. So that's the two resonant frequencies. And so that's an example of what you can do beyond just simulating, changing parameters, simulating again. So you can do post-processing on the results and create additional value and information from your model. The last example, looking at time, that I have is a more complex model with more rollers and more web, and that's an accumulator. This is not a very sophisticated design here, as there is no controller embedded. It's basically says consider the velocity of the input, velocity of the output, and then the difference of that will be, and with some gain in algebraic form, will be how we move the accumulator up and down. So this is the plan that we have for this simulation. Every 10 seconds, we're doing something. And to accomplish this elaborate plan that we're going to stop the in-feed, out-feed, and things like that, use one of the MapleSim apps. And this app is for signal generation. So I basically created two signal, one for exit speed and one for entry speed, and I can plot them on top of each other. So the scenario I'm emulating here is that I have a web line, but I need to remove the rewind drum. So during that time, the accumulator has to absorb the web and then do the other side, come to normal, and then remove the unwind drum. Maybe it's depleted and the new one is going to be placed. And during that time, the accumulator has to provide the web for the continued operation. It's a longer simulation, so I'm just gonna maybe speed it up a little bit, 8 times. So now we're going up. The outside, the rewind is stopped. Now the unwind is stopped, and it comes back down. So this is a model with a lot of span and a lot of pieces. MapleSim can still simulate this very, very quickly to give you an indication of the efficiency of what we export from this type of system. And this is the most complicated model that I had. That's the one I've chosen to use the FMI and the Insight example. So as I mentioned earlier, one of the applications that you might have with our technology is to build a digital twin of your system, and then within your PLC, test your controller against, instead of a real machine, against the virtual representation with the fidelity and the aspects of the system that you have included. And that is, in most cases, accomplished by using the FMU, functional markup unit. FMI is the standard that a lot of tools now support. A lot of automation vendors also support this technology. For this demonstration here, I'm actually using MapleSim companion program, MapleSim Insight, which allows me to test the FMU that I've created. Insight can work with automation software as well and provide the way for them to stream data to it and see the results as the PLC is working. But in this case, I'm using the Insight to actually run the FMU and interact with it in a live fashion. Instead of setting the parameter, running the simulation, seeing the results, I'm going to be doing that live. So I have the FMU. I'm just going to open that in MapleSim Insight. So this FMU was generated previously from the model, the accumulator model. And now we are in MapleSim Insight. When you run a model in MapleSim, the equations are generated and the simplification phase is applied to it. Here we have a compiled code, so there is no waiting. You get your results as you simulate your model. So let me turn off this one and turn off this one. So this is my model. It is ready to go. So I just, when I was generating this FMU, I've included some tunable parameters. I'm gonna let it run. And I'm actually syncing the outputs with the clock. So this is gonna be pretty much look real time, because the integration is faster. So I'm slowing it down to match the clock. So I can now change, for example, if I reduce the exit speed to half, then the accumulator will start to absorb the excess material. I can go all the way to 0, and that will just speed up the way the accumulator getting more. And you can see that this side is not rotating at all. So let me put this back to normal, which causes the accumulator to stop. And obviously, we can guess what happens if I do it the other way. So I'm interacting with this. This interaction can take in many different shapes or form. Obviously, this can be the part that your controller interact with instead of me manually changing that. But the message here is that the model is created in MapleSim, the code is generated, and that code is available for digital twin applications.